Hello, welcome to another problem session. Um, this is a problem that has a lot of different concepts involved. Um, so, we'll try to set it up. It says center of mass motion, momentum conservation, and kinetic energy conservation as well. Energy conservation, not just kinetic energy, just energy conservation as well. Okay, so it comes from a kind of competition or a test in India. It's called JEE-Advanced. It was in 2017. I really like this problem. This is a really good problem. So here is there are two things moving. Actually, this wedge, I can call this wedge, which has a circular edge on one side, and there's another block, and this wedge, both are moving. Actually, both will be accelerating when you let go. So at t equal to 0 is over here, and this guy has v equal to 0, and this guy has v equal to 0. So that's the way it starts. Here is a coordinate system which is not fixed to anything. If anything, it's fixed to this table, frictionless table. So say this is the y-axis, and this is the x-axis. When this thing comes down, so this block is moving to the right, so the wedge will actually move to the left. So let's see if the center mass of the wedge was over here. So this big M was over here at this point. Let's call it x0. So when this thing moves, at some point this block will be over here. So let's take a different color here. It's over here, and it's going to come out horizontally with speed v. Okay. At that time, this entire structure would have moved because this wedge underneath has moved. So actually, that's not going to how it will be. If you redraw, suppose you redraw the picture over here. So this is this was the original place. Then the block would have moved out here, and this coordinate is x when it's coming out. So that's what the description says. And so this x0s were over here. Now the center of mass is over here. So this distance must be equal to the same distance as that, because this is a rigid body, and so if we move the whole thing at distance x, the center of mass will move to a distance x. So this also x. So this is the x0. Let's call it x at this point. Let's call this xcm, this x. There are no external horizontal forces. So if you look at these two together, there is no horizontal force. It's frictionless. Right. So if you look into little mass plus big mass as one system, so let's see this guy and this guy. So it's initially the center of mass is maybe over here of the so it's, let's call it XCM of the one system whose center of mass is at XCM. This together, okay, on the x-axis and YCM. So over here is the YCM. We're not going to be concerned with YCM, but suffice to say that when you look at the XCM equation of motion for XCM will be d square XCM dt square and m plus big M, total mass equal to XCM, then this should be equals to the x component of any external force on it. And because this is equal to 0, no force, that means it has a 0 acceleration, which means Cm is constant. That means which is actually initially at t equal to 0, it's not moving. So this is equal to Vcm at 0, which is 0. That means Xcm is fixed in time. But Ycm is not fixed in time because there's a force of gravity down like that. M plus mg down like that. So you can see Ycm used to be there, but when it exits, Ycm will be a little bit down below. Okay, so the Ycm will be not at the original place. So Ycm does move because of gravity. Okay, but actually we don't have to worry about that in this problem. But this is a very important observation, and we're supposed to figure out what this x is. And if you look at the B, it says x component is the center of mass of the block. So we're supposed to figure out not the center of mass of two together, but this m. So figure out x, what x will be. Well, from the geometry, x is just x0 plus x, right? So x is actually equal to x0 plus x. This is more. So if this is negative and this negative, is going to add up to become a bigger negative. Okay. So that's the question A and B. So I'm going to decide on that based on what I find by this logic about XCM. So it seems that XCM of the whole system at 0 time should be equal to at this time when it leaves. Okay, XCM of the whole system at time t. And when you set this up, we should be able to get something to decide between A and B. Maybe both are right or both are wrong, or maybe one of them is right. So let's see, at this point is x0, mx0, and x0 equals to minus r. If you look at down here, this is on the negative x-axis, and this is the minus r, plus big M at x0. So big M at this point, x0, the way I had defined. So that should equal to little m, and when it moves it at this point, little m is at coordinate little x, plus big M is at capital X, which is x0 plus x. So it turns out that this part is cancels by that part when you open the parenthesis. So this side is m plus m, x, and I can solve for x and put this in there. X is equal to m over m plus m minus r. And when I look at this, of course this is wrong, so this is not right, but this is correct. Okay, so this is correct if we say that if we say that I'm looking for little x, okay, but if we are saying where the center of mass is, then this will be different. But this asking displacement, how much it has moved, center of mass used to be here, how much it has moved, it's really asking for x. So this is correct. So B is correct. So A is wrong and B is correct. Okay, so we decide between A and B. Decide between C and D. We will have to use velocity concept. So again, if I look at x direction, then this says center of mass velocity is also is actually 0, which means I should get along the x direction so we're supposed to solve for point mass or big mass. Okay, so we sort of figure out the velocity at this instant. So let's see, is velocity distance is v that way, and this guy's velocity is, let's call it capital V. And you look at x component, and this is the speed here on this direction, and this guy's speed is with the velocity in that direction. So if I look at m little vx plus big M little vx, and this at time t should be equal to same at time 0, and that should be 0. So if I use this symbol, I got mv minus m capital V equal to 0. Okay. Of course, the velocity, x velocity, this guy has positive and this guy is negative. So this, let's call it equation 1. Now, if you look at energy concept, then whatever the energy is here must be equal to energy here. Why? Because all the forces that are acting on it, there's no friction acting on it. External force is normal and gravity, and normal force is not going to do any work. The gravity work is taken by potential energy. So energy conservation will give me, very interestingly, at t equal to 0 versus t equals to t versus t equal to 0. So at t equals to t, this guy is moving with speed v, and this guy is v, and this guy's center of mass has come down here. So let's see, we call this at 0 for potential energy, that level. Then this level will be mgr, because this is a distance r, the radius of the arc. So little mgr, that's the potential energy at time 0. I'm sorry, this will be mgr, and on the left side will be potential energy will be 0. Kinetic energy, this will be half little m v square little v square, and plus kinetic energy of the big M v square. Now we can use these to solve for little v and capital V. Okay. So let's see, I want to solve for little v. So I just plug in here. So we'll get 1 over 2 capital M and little m will v square plus this equals to plus this. So that's going to be v square equals to, m will cancel out from both sides. So that will be GR. 2 will go on the other side, and you will have a m square here. So m square plus m, one of the m got cancelled out, and so I will have 2gr, and this will be little m over m, and that guy will be 1. And so if you take a square, this is speed, it's a square root, and sure enough, this is correct. So C is correct. To check D, I need to just do capital V, and it's asking for velocity, which is v, asking for v sub x, and which will be negative. So solving for v will be m over capital M times v, and so m over capital M is square root of 2gr over m plus m, and then you can say m, and so this m will cancel this guy's square root of m, and so this look nothing like that, so that's not correct. So we just have B and C as the answer. This is a very tricky question. There are several things that went on here. So let's just go over them just one more time. After every problem you do and you're practicing, you should go over them. So when I'm reading this part, they all has to do with x. And the catchphrase here was displacement. So drawing a picture, and even if I don't know this x0, it was important to actually introduce this center of mass for just the block itself. So it was important to introduce, although the argument for the net center of mass is important, but it was important to introduce x0 equals to center mass of block itself at t equal to 0. I find that to be my main thinking when I was trying to come up with a strategy for this problem. When I was reading this problem, the very first thing occurred to me, hey, let me get the center of mass of the block itself, and then I will argue from there on. So that was my linchpin of my thinking. And once I got that, then I identify the principle that will be involved. And I explained like this, but it did not take me all this argument. Much of this, you have to do it in your head. You don't have to write this, but because I'm trying to explain to you, this thing was immediately in my head. And then using this x0, I was able to get x0 plus x for this, how much the center of mass would have moved. So that this is where the center of mass is decided by total mass. So if you look at xcm of the total at 0 will be this stuff divided by m plus m, right? And center of mass of the total will be at this divided. So this will be xcm at t will just be this guy, mx plus big M x0 plus x divided by m plus m. I didn't use this, but I was able to come up with this formula because denominator will be this total mass. So that was a simplification. And once you realize that, the rest is really nothing. After that, getting the x and getting that this b is correct and a is not correct is quite simple. Between C and D, I really had to kind of identify momentum conservation and energy conservation, and this was not that hard to get. But momentum conservation has one problem here. If you mess up this, you'll mess up the sign here. And then actually, if you mess up the sign here, you might not get into trouble. I don't know, because you might make two negative signs mistakes, okay, and then you recover. But I feel like you should always think of momentum conservation in terms of coordinates, so you don't mess up sign. Okay. All right. That's it for now. Talk to you another video. Bye.